Hi, we're the Multirotor Design Team here at Missouri S&T. We're an entirely student-run organization here on campus and currently consist of over 80 active members. Our team's made up of 4 main divisions: hardware, software, business, and racing. Each of these divisions has their own unique specialty, and we're super excited this year to be attending the SUAS competition.
I'm not ready yet, ready to begin.
Here you can see a picture of our development team taken at our 2024 drone reveal. Our team is made up of students from all different kinds of disciplines, and now we're going to introduce you to our competition team.
I'm not ready yet.
We looked at the rules and we decided that it's going to be a very long flight, so we're going to need a lot of battery power and we're going to need a lot of props. We're going to be carrying a payload, and this is going to be a heavy drone. So we went with 6 props.
On our ground station, we have Q Ground Control, which provides us with a map of the competition space, as well as some information that we need for ourselves and for the judges. But we also have a few different scripts running on our ground station. One is a Mav proxy radio script, which allows us to see a live stream of all the data that the drone is receiving. There's also another Mav proxy shell that we utilize to monitor a few different parameters that are not within Q Ground Control. So ground speed example is one that we need for the competition, but Q Ground Control doesn't provide for us. So we need to have another set of information on the ground station for the judges.
For our SUAS drone, we have verified these results by testing our drone at 15 miles per hour in the field, which netted us a flight time of 30 minutes. We continue to test speeds to find the most optimal flight time for competition.
Our drone uses 3 different methods of control. We have the transmitter, which the pilot will be holding, and I can give it manual inputs of how to change its direction, heading, and get it back out of a difficult situation. We also have the ground station operator controlling the ground control software. So he can click a point, make it go there, as well as return to launch if it gets into a rough situation. And then the main competition is going to be run through our flight computer, which is an onboard computer sending Mavlink messages back and forth from the autopilot to communicate where to go, how to get there, and get data back on GPS coordinates, altitude, and read different sensors that are connected to the autopilot.
In order to make sure that the photos that we are taking using the camera give us accurate location readings, we use certain deskewing and offset algorithms to make sure that even if the drone wasn't directly above the object when the photo was taken, we can still use the location data from the drone in order to get an accurate location reading. First, we deskew the image, which means we translate the photo taken at an angle, turn it into a photo that looks like it was taken from a top-down perspective. We use trigonometry and the data from the drone's angle and altitude in order to convert that angled image into a top-down perspective image. After the image has been deskewed, we use offsets, basically using the camera's focal length and the drone's altitude in order to convert distance in pixels to distance in feet, and add the offsets to make it the location of the object. In order to ensure the optimal image quality for the pictures that we are taking from the drone, we've adjusted the settings on the camera in order to give us a clear photo of the objects. One of which is adjusting the zoom to be at max so that we get the highest resolution image of the objects that we could from the camera. We've also adjusted the shutter speed to be very high so that it counteracts the movement of the drone as we move through the air. It means we'll have less blur. In order to test different settings on the camera, we've flown the drone up at the competition altitude that we'll be taking photos at during the ODLC object detection state. We've picked the best possible combination of settings.
So for our standard ODLC testing, what we do is that we actually cut out a couple examples that might show up at the competition with random shapes and random colors, and have cardboard cutouts with them taped to prints.
For payload delivery, we decided to go down to 2 bottle capacity, and we'll just do multiple landings to complete the mission.
This is also another 3D printed component. It's made of TPU, which is a rubber-like material. It's very squishy, and so it's very impact resistant. On the dropping mechanism, the servo connects to the flight computer, and it tells it when to pull the arm, which releases a pin, which will release this bottom part and allow this to come out.
For testing the water bottle drop mechanism, because we have a UAS platform, we're allowed to actually just hover over the target and then release the water bottle at any given command. So how we do this is that we actually have a state machine code running on the drone that senses that once it's at the specific GPS location needed, it releases the water bottles and then floats perfectly onto the ground.
All right, so our drone is controlled with manual input through ELRS, which is a low latency, high range device. We've actually used this in not only this competition, but in previous years in the Argonia Cup, where we had it connected to the transmitter while it was in a rocket going up to 10,000 feet, and we didn't have any connection issues then either. It's running 2.4 gigahertz, and our telemetry radio we're also using has 915 megahertz, and we're running about 500 milliwatts on that. The ELRS transmits digital RC control messages, and these messages are translated to analog to go into the input on the carrier board of our drone. Our telemetry radio uses a digital data of Maverick to transmit messages from the ground control to the actual drone, and as well as our flight computer sending those digital Maverick messages to the autopilot.
To monitor and test the communications of the drone, we've tested both the range and the packet loss and throughput of the drone and all the communication that goes on it. For the range of the drone, we are testing it by observing the telemetry of the drone as we drive further and further away with the drone from our receiver. And to observe the packet loss and throughput, we've monitored that throughout doing our partial and full mission tests and just observe the data while we do those tests to see the packets as we perform different actions with the drone. You can see the results of these communication tests here.
Here you can see a diagram of our communication system. So you can see that our current setup is a hexacopter X, which means that it doesn't have an arm in the middle of the front, it has arms in the middle of the sides. On our top layer, you can see that we have our GPS, telemetry radio, and remote ID module, so they get the maximum range and visibility. As you go down, we have our autopilot, which connects to all of its ESCs, which go out to the motors, as well as our Express LRS to give us the remote connection, and our servo connections on this layer. On our bottom layer, we house our batteries, our flight computer, as well as our camera to take pictures of the ground and the ODLCs.
For propulsion, we're using 20-inch carbon fiber propellers that have specially constructed tips that will reduce the vortex and increase the stability of our drone. We're using agricultural drone motors that have a kV ratio of 340, and they're 3-phase power motors.
At the center of our electrical system is the bike carrier board and an orange cube at the very center. On the screen now, you will see a wiring diagram of our electrical subsystems.
We've also done connections with the cameras as well to make sure that we can run all our camera code on board and then also be able to see the output on the ground station. We've also done a couple state machine unit tests as well, which include running our waypoint state machine code about 8 times on our competition drone. In terms of the flight performance requirements, we have run the 5-mile waypoint test fully loaded for our aircraft multiple times, so we've met that requirement, and because we are a VTOL UAS aircraft, we meet all the other requirements associated with that, which include the waypoint error of 25 feet, the turn radius of a maximum of 150 feet, the angle of climb and descent of 20 degrees, being able to stay above the 75-foot AGL at all times. We will be using a max runway size of about 6 feet by 6 feet, which we're allowed at 70 feet by 70 feet. Here you can see the table of all of our aircrafts and their full flight times. This includes our competition drone as well as all of our testing platforms that we've used for competition.
Taking a look at the software side of things, we utilize PX4 as our primary firmware for our flight control. Our ground station has Q ground control, which we use to monitor the drone's position, as well as provide us with a few updates on the certain drone parameters and information that we need. The software is organized with 2 different hardware devices on our drone. We have a cube, that we have our firmware loaded onto all of our PX4 firmware. We also have a onboard flight computer, a Jetson TX2, which we utilize for our more complicated computations, primarily for our vision algorithms. The Jetson allows us to do onboard computation, so we don't have to do large-scale data transfer from our ground station to the drone. We run all of our code in 3 separate processes, 1 for our flight code, 1 for vision code, and 1 for obstacle avoidance. The flight process allows us to run the full state machine with our waypoint code, The vision process allows us to run all of our ODLC detection and classification code. The last one, the obstacle avoidance process, takes the information from the ultrasonic sonar sensors and will maneuver our drone in small movement bursts to allow us to avoid other obstacles or aircraft that might be in the air.
The state machine is the foundation of all the autonomous code that we'll be running during the competition. It consists of high-level logic to run the corresponding state code depending on what phase of the competition we are in. The first state is the start state, which just connects to the drone and makes sure that we have a stable connection to it. Next, we have the takeoff state, which launches the drone up into the air from the dedicated takeoff zone for the competition. We have the waypoint state, which runs through the waypoint lap that will be given at the competition and make sure we hit the corresponding range to each waypoint. We have the ODLC state, which detects objects on the ground using photos taken from our camera and uses vision logic to try and detect what object that is, what color it is, what letter it is. Next, we have the airdrop state, which takes the locations of the objects found in the ODLC state and drops the corresponding bottle there. And then lastly, we have the land state, which just lands the drone at the takeoff and landing zone.
For obstacle avoidance, we utilize ultrasonic sonar sensors in order to detect other aircraft. These are relatively small hardware devices that we mount on the ends of each of our arms on our drone. Now, in terms of algorithms for obstacle avoidance, we can utilize some off-board commands to make some quick adjustments to the drone's position. In the event that an obstacle is detected, our general strategy for that is to move more in the 2D space versus the 3D space. We'd rather not fall below our minimum altitude threshold.
In order to integrate obstacle avoidance into our state machine, we've implemented the same code that we use for our manual takeover into our obstacle avoidance code. In order to test our obstacle avoidance on the drone, we've flown our drone up into the air and flown other smaller drones nearby the drone in order to see if our sonars would pick up the detection of those objects. We can monitor that through our ground station, and we've tested and made sure that our sonars do work and do detect other objects in the air. We've also tested the off-board functions that we'll be using on the drone, which moves the drone a certain distance in a certain direction, and we can use these functions in order to move the drone away from whatever object may be in the air.
Throughout the design process, there are multiple design considerations that were not included in the final design. One problem we had was with the arm mounts. We decided to initially use plastic, but they ended up breaking a lot. You could tighten them down too much and they would just crack, or the arms would rotate a lot if we had a crash. So we decided to go with aluminum so that they didn't break as much and they were more robust and lasted a lot longer. They didn't rotate as much.
So for the competition this year, we decided to write the majority of our code in Python. With other languages like C++ or C, you have to do a lot of complicated memory management, but with Python, it's a lot easier to manage these larger data structures, and it allows newer members to pick up these functionalities relatively quickly. Regarding obstacle avoidance, we had the choice of two different hardware devices. Now, we settled on an ultrasonic sonar sensors, but we were also considering a spinning LiDAR device for obstacle detection.
To mitigate any risks that could be associated with the manufacture and assembly of our drone, we have put several steps in place to prevent any issues with our members getting hurt. One of these methods is using XT connectors that don't arc. To mitigate risks when we're actually in the air, when we're flying, we have a set flight line. So the pilot will be that front of the flight line with the ground station operator right next to me. All of our pilots are 107 certified and go through training before flight.
An overview of our partial mission tests include our defined state tests for our state machine. These include the waypoint code, the ODLC code, and as well as our airdrop code. After running over 200 waypoint tests, we only have about 3.8% error with our waypoint code. Our simulation subteam on our software side verified that our ODLC and our airdrop code works 100% of the time within the simulation, and we'll be integrating that into our physical platform before competition. To prove that our water bottle drop mechanism works, what we did is that we tested it 5 times out in the field, that we were able to review the data and see that we had an 80% success rate with a 90th percentile of 22 feet away from the target. After analyzing all the tests we've conducted, we predicted that we would achieve about a 67% completion of the full mission demonstration for the SUAS competition.
not ready yet. I'm not ready yet.
Thank you all once again for considering our submission for this year's SUAS competition. I hope that throughout this video you've enjoyed getting to meet some of our chief engineers as well as the hexacopter that we've been prototyping for almost 2 years and are super excited to see the full extent of what it's capable of. We operate with a high level of operational procedures and testing techniques that we hope will give us a competitive advantage at SUAS this year. We look forward to seeing you all this summer in June.